Good morning to all. We would like to welcome to all participants are joined us online, and also we would like to welcome the participant in person here in Turin, Italy, in the second pilot demonstration. So we will give some information to you all to have a smooth meeting. My presentation is not moving. Yes. So we would like to ask you all to mute your microphone and also turn off your video if you prefer to leave your video on. It's also good for us. If you wanted to interact on the if you wanted to interact on the meeting, please write us your question in the chat box in your right side. And as you heard, the meeting is recorded to use it in purpose of the dissemination activity. And this is the agenda you plan to have today. So we start now at 9:30, and we have a few of colleagues are here present to show us your presentation, your work on it, and also you have some presentation will be by remotely system. Thank you very much for your participation with us. And please, if you have any questions, do not hesitate to send a message on the chat to us. And now I welcome Maria, the project coordinator of Resist project, to present her presentation to us.
Okay. Hello, everyone. Hello to the ones that are here in person. Hello to the ones that are connected remotely. Thank you for joining. These days we have the final pilot demonstration, the second one that's conducted in Technostaff premises. So today in this workshop, we're going to present you the components that have already been developed and how they have been integrated to provide, let's say, an holistic approach for the preventive and predictive maintenance of infrastructure. So let me start with a brief, let's say, presentation of an overview of what is Resist about. It has been submitted under the topic resilience to extreme natural and man-made events. It's a research and innovation action with a total duration of 46 months and a budget of up to 5 million euros. It is coordinated by the Institute of Communication and Computer Systems in Greece. And the consortium is consisted of 17 partners from 9 countries, including the 2 infrastructure users, the Egnatia motorway in Greece and Technostaff motorway here in Italy. Here you can see the distribution of partners all around Europe and not only Europe. So we have partners from Italy, Spain, Belgium, Germany, Luxembourg, Austria, Switzerland, Israel, and Greece. Let me start with the concept of this project. So even if we have great achievements in the field of transportation, the infrastructure are still, let's say, can be affected seriously from extreme events that may put human lives in risks. These events may be caused by natural causes, for example, earthquakes, floodings, etc., physical causes, or man-made events, or even cyber attacks. So the objectives of Resist project is to obviously to protect users and ensure that the mobility will be seamless, avoiding, of course, any human cost, but also financial costs as well. To prevent and predict such events and also increase the resilience of infrastructure through vulnerability and predictive analysis and risk assessment, and also to react in such events, providing information to minimize the impact of the event and restore the services as soon as possible. Here are the innovation of Resist project. So we have the aerial robots, some drones, let's say, custom drones that are used for inspection and also for mounting sensors on bridges and tunnels. We have the ultrasonic sensors that are suitable for these drones, the computer vision system, secure and resilient communication system, a cross-labor cybersecurity module, a mobility continuity module that is focused on providing seamless mobility for passengers and freight, even under extreme events, a risk assessment and management of such extreme events. And all these are combined, let's say, in an integrated Resist platform, providing an holistic approach to all these procedures. Okay, here is the project architecture. I know this is a quite dense slide, but let me provide you some key points. So in the upper and right part of the slide, we have the sensor data from sensors that maybe are already mounted on the infrastructure or may be mounted through the drones. On the upper left side, we have the drones that collect information and data from these sensors. In the middle, we have the communication layer. Through the Redcom module, all this information are transported to our platform. And then we have the application layer where we have the risk assessment, the vulnerability assessment, situation awareness, mobility continuity modules, and so on. Of course, we have a cross-layer cybersecurity module in order to avoid and identify and avoid cyber threats and provide, let's say, the most increased security to our system. Okay, the validation of the system is going to be conducted. Actually, it is conducted in real conditions and infrastructure. The first pilot was conducted in Greece, in Bridge Staff 9, in Egnatia motorway. While the second one is these days in this pilot in Technostaff premises, A32 Mioris Viaduct and St. Petronilla Tunnel. So this is it from my side. Thank you all. I think now we will proceed with the presentation of all components that we have, and you may have more information for each one of them. And then we have the time to discuss about them. Just a slight change to our schedule. The next presentation was about to be about the drones, the Rpas system, but we may delay it a bit. So we'll proceed with the next one, the ultrasonic sensors and computer vision systems. So let me ask our colleagues from CNR to proceed with their part. Thank you all.
Thank you, Margarita. Thank you. I'm Luca Belsito. I work at National Research Council of Italy. We are in charge in this project for the development of the contact sensors. In the project, we want to realize three kind of measurement. Basically, it's a crack depth measurement, a crack width measurement as well. And also the drone has to have the possibility to install permanently a sensor. In this case, we want to install a accelerometer, 3-axis accelerometer on the bridge or in the tunnel to transmit the data wireless and acquire the vibration mode of the structure. Then there will be Rafael and other colleagues talking about the vision system. For the crack depth measurement, the idea is really simple. It's something that is already done commercially. We use two piezoelectric transducers, one transmitter, one detector. When the acoustic wave generated by the transmitter propagates across the concrete, it's then reflected by the bottom of the crack, and then is detected by the receiver. By measuring the time of flight between the transmission and the detection, we can easily determine the depth, and the ultrasonic speed is measured as well in a region close the crack. So it's just a simple Pythagorean theorem to determine the depth. Instead, the idea for measuring the width of the crack Of course, there is also the vision solution where for determine the width of the crack, but we want also to realize some contact sensors to measure it. In this case, the idea was just to realize an optical performometer that is a scan around the crack, really close to the crack by the drone, to determine the profile of the concrete and so determine the width of the crack. And finally, we have developed this low power vibration module with a sub-gigahertz communication, so wireless communication to increase as much as possible the battery life. And this vibration module communicates directly with the receiver that is on ground. Here we can see we have realized this on the left. This Parser receiver unit is a custom solution because in the market we haven't found something with the specification that was needed in the project, because we wanted to have something with the possibility to tune the frequency, so to use several transducers, at the same time to have an actuation voltage between 300 to 3 kilovolt to use also powerful transducers. That is really important in the measurement of the depth in the crack. And also we have integrated a high resolution time to digital converter, so to measure with a really high precision the time between the emission and the detection between the transmitter and the receiver. Also, this kind of system has a USB communication, so can be easily controlled remotely by using the PC on the drone. On the right, we can see the integration of this kind of system and two different platforms. On the left, on the top, we have the end effector realized by the CATEC in Spain. This is used for the bridge inspector. And on the bottom is the platform realized from the University of Seville with the integration of our module for the tunnel inspector. Here we can see just an example of acoustic wave detected by using this custom Parser receiver unit. You can see the signal is really nice with low noise. We can determine easily the time of flight, so the time between the transmission and detection and determining the crack. So instead, here we can see the idea for the optical performometer. Basically, it's a simple optical phase measurement, indirect in particular, like a LiDAR system. We use a modulated laser source that is used to interrogate the target. Then we measure the optical power reflected by the target by using an avalanche photodiode. By comparing the phase of the transmitted wave and the detected wave, you can determine precisely the distance. In this way, with the translation stage inside the module, we can scan around the crack and determine the width. We started from a commercial range meter that we have modified in the firmware and in the optics to reach the specification that was needed in the project. In this case, we wanted to determine the width with a precision of 0.1 millimeter. So also the spot diameter of the laser has to be less than 0.1 millimeter. So we changed the optics. We go with the drone really close to the width, because the right distance is the focal length of the lens that we use in the system. And we use also the Gauss algorithm to determine the phase shift. In this way, we can determine really precisely the width. We have successfully validated this kind of measurement in the drone realized in CATEC. Here we can see a measurement realized on an artificial crack sample of concrete there on the left, and on the right the measurement where we have developed a user application when the user can set all the measurement parameter like the power of the laser, the sampling frequency, the algorithm they used, the parameter of the Gauss algorithm to use in the measurement. And we have successfully measured the width for crack up to 0.4 millimeter, and we have validated flying on a larger crack. Here is we can see the idea for the vibration module. It's really simple. We use a 3-axis accelerometer from analog device. It is a 3-axis accelerometer with a really high signal to noise ratio. with inside the digital conversion. The user, by means of a user application, by the ground station, can set all the measurement parameters, like, for example, the acceleration range, the sample frequency, the cutoff frequency of a low pass, high pass filter that can be used inside the electronics. And in this way, we have created a really small network where each vibration module has an address and can be interrogated by the receiver on the ground. This module exploits wireless communication with a sub-gigahertz communication, so we can have real-time continuous measurement for more than 3 days. But of course, if instead of measure continuously, if there is only some time during the day, that we can have a battery that will, with a battery life of months, also here, depends on the frequency of the measurement that you want to realize. Here we can see the integration on during the Mesovo trial. Here on the left, you can see the LED. Basically, the drone attached this vibration module. This is really small. It's less than 40 grams with a diameter of 5 centimeters on the wall by using a UV curable glue. So we stay on the wall just for 10 seconds for gluing the module. And then at this point, the module starts communicating with the ground station by, as I was saying before, by sub-gigahertz communication. So there is a continuous communication. So the user by the ground can set all the measurement perimeter and so on. Here we can see the user application that we have developed. On the right, it's just really simple. We can see the 3 axes of acceleration with acquisition on real time, but there is also the possibility to plot the fast Fourier transformer of the acceleration data. So to see the vibration mode of the structure that you are investigating. Now, Rafael can continue with the vision, or someone else. Guillermo gets here. Okay.
Okay, so let's go back to our schedule with the presentation of the RPAS. Just give us 1 second to change the presentation. Okay.
Okay, good morning. So I'm Guillermo Heredia from University of Seville. So we are going to present the aerial robots, or the Pastor drones, that we have developed in the project for installing the sensors that you have seen before from CNR, and you will see later for inspection of the tunnel surface. So the general idea of the project was to develop not a robot, but a flying robotic system, because there are several sensors that have different needs. So at the end, the main sensors, we have decided to use 2 different aerial robots. One is for the visual inspection, so that we will mount the camera module, and the other is for contact inspection. So the one for visual inspection is a quadroton drone with adaptations. We have installed a gimbal for camera stabilization and orientation that is installed on top of the drone, so it is adapted to inspect all the inner surface of the tunnel. And also, an important point that I will talk later is it uses the localization system inside the tunnel for autonomous controls that it can follow the waypoints of the flight plan that it is transmitted to it. The second one is a drone for contact inspection. So this is a new design that is adapted to the inner walls of the tunnel. Okay. So the idea is that it is able to touch and attach to different parts with different inclinations of the tunnel, and with the sensors that are mounted on the tool, it is able to sweep into D. So it is able to do linear motion, and also in the curved direction, just to inspect the surface or to look for defects and measure there with more precision. And it is able to mount the ultrasonic sensors, or the jump module sensor, also the rebar detection sensor, and also cameras. You can see here the general configuration of the tool. So there are two. It has three servos. Okay. One is when it's moved on this around this curved dimension. The other one in this linear direction, and the other one it is used to that is this one. Sorry. Okay. Okay. Yes, this one that is used to adapt to the different inclination of the tunnel walls. Okay. This is the first design of this class, and that it is used for inspection of the tunnel walls. You can see here some experience. The idea is that with these supports, it is able to touch the different inclinations. So in this part, it would be higher, and with these two supports, it would be even higher. And you can see here that this is the image of a camera that is mounted on the cart. But there we can mount any of the sensors that we are discussing today. Okay. Then an important point is the localization. So for autonomous flight, it's very important that the aerial robot knows in any instant where it is in relationship with the environment. Inside the tunnel, it is not possible to use the usual methods for localization, like of course GPS or DNS, or even the vision-based or leader-based SLAM techniques, because of the symmetry that the tunnel has. It is impossible to use them because it gets confused about the position. So we have developed a localization system that use on one hand a total station that calculates the position to a priest on board priest and transmit it to the drone, and also some onboard sensors that are two 2D LiDAR sensors and one range sensor. The 2D LiDAR sensors are used to obtain the relative position to the transversal to the tunnel. Okay, you can see here. This is the output of the output of both lasers. One is this curve that this is the transversal position, and the other one that is in the horizontal position just is used to obtain the distance to the world. And with these two, it is able to localize in this transversal plane, and also to drive and close the loop to be able to touch and autonomously attached to the surface. The other one, that is a range sensor, it is used to obtain the position along the tunnel line in the longitudinal position. And that's it. Well, just to tell you that in this case, this is another robot that we are using for navigation and testing and validation of the algorithm, but has the same functionality of the larger one, but without the card, and it is lighter and easier to use. Okay. So its presentation.
Okay, thank you, Guillermo. So now we can proceed with all the computer vision systems and modules. So let me open the new presentation and call Rafael Valharter to present it. Okay, thank you.
Thank you, Marita. I'm Rafael from the Technical University of Graz in Austria, and I'm going to present the photogrammetric computer vision system. So our system consists of several components, which is firstly the stereo sensor, which is used to capture and store the images, and this is directly mounted on the drone. Secondly, we have the system in the field, which is used to generate depth data from the images. This is basically our core system, where also all our research went and where our publications happened. And finally, we have a web-based viewer to present the results we generated to the user. This includes our data, our 3D data, and the defect detection done by the University of Frankfurt. So we go a little more into detail, the hardware components. On the right side, we can see the stereo sensor mounted on the drone. Its main components are two high-resolution cameras with internal wiring for synchronization and an onboard processing board. So the system in itself is a standalone system. It's just controlled by the drone, but could be mounted on any robotic system or any different drone. And on the left-hand side, we have our so-called system in the field, which consists of a regular laptop with an eGPU, so an external GPU for processing power. This is used to run our machine learning algorithms, which use a lot of memory directly in the field. And each of these components has its own software. So for the image capturing software on the sensor, as I mentioned before, there is its own processing board, so it can just store the image directly on the drone and will then be transferred via hard drives for an easy and fast transfer to the system in the field. And the system in the field, secondly, is where we run our machine learning algorithms to predict 3D data from 2D images. So these are deep neural networks, which we trained before on all 3D data. And now it's able to calculate depth from 2D, like in a few seconds. And finally, as mentioned, we have the web-based 3D model viewer app, which you can see here, and we'll later get a video on how this interacts with the components. Thank you.
Thank you, Rafa. So the next presentation, we will have our colleagues for our group who will present it online.
Can you give me access to the screen share?
Yes, you have it.
Okay, thank you. Okay, I'm Viswanathan Ramesh. I'm from the Goethe University in Frankfurt. We did the computer vision part. As already mentioned in the beginning of the whole presentation, the whole architecture involves essentially taking the drone-based images, sending it to 3D reconstruction and getting stereo data, and then essentially doing analysis. The main aspect of what we have been doing in Frankfurt is to build a composable toolbox that allows you to deal with a variety of situations and essentially flexibly able to use our modules and compose them so that we can actually perform the inspection task. And it has certain kind of parallels to human intelligence and the way in which we think about cognition. Now, what I'm going to do is quickly show some of the work that we've done in the context of resist, and also what the results we got from the particular pilot. So we have actually a variety of different modules which address various aspects of actually visual inspection, which go all the way from using physics-based models and understanding what are the properties of the application in the physical context, and then using them to actually build essentially algorithms where actually expert knowledge is embedded so that you can actually reduce the amount of data required for analysis, or in other words, for even training and learning. Then there is the other side of the equation, which is actually that we need to have invariance, meaning that we need to be invariant to lighting, weather, other conditions, and therefore we need actually robust methods. So therefore we have a modular approach where actually we can essentially implement multitude of modules, each addressing sub aspects of the problem, and then they're all basically running in parallel and then they combine. So here you see in the toolbox, there are these 6 boxes. Some of it actually were extensions from the PROS project ROB. For example, the topological pit extractor was adapted and extended in this project. And then there was new domains, new modules, for example, multitask learning, and then this idea of basically building on-the-fly models from the particular image instance so that you don't have to do large-scale training. And then the idea of actually multi-target variational inspection, which again is borrowed from ROB. And then the exploitation of 3D data, and then simulation for inspection of steel bridges. So these are the concrete aspects that we have essentially built. So here is some illustration of the way the system works. So you can see that the physics-based models that we can use, given an image like this, you can actually produce hypotheses. So we think of each of these modules, parallel modules, producing hypotheses. So here you can see that in this particular image, you can get a lot of the cracks and also small defects, which are not necessarily defects. And the point is that cracks are essentially treated like fractals, and they are connected, and they are anisotropic. And then one of the major innovations that we have actually done in this project essentially is this idea of using just one image instance, using these model-based ideas from physics-based models, combining them with modern deep learning, where the deep learning method actually learns the background texture from a single image. So what we do is that we take a single image and then we actually produce some response like this, and then we use that response to mask the image and then say, okay, to the neural network, learn actually the background pattern as much as you can, and then try to fill whatever you don't see here. So in a sense, it's more like saying, okay, I have an assumption about the world, meaning that the texture is continuous, and that texture you learn from that particular image, and then you compare them. So effectively, it is more like a background subtraction. So this is what we have done. And here is an illustration of that work where you have the original picture, and then you can see this neural network learning actually the background estimation, and then the difference coming out. It's okay. Now, then you can see certain results on real data sets. Then I'm going to skip that. And now there is the other angle that was basically a novel innovation in this project. That is actually the fact that we now use 3D data with the TU Graz. So therefore, we can actually think about how 3D geometry, along with actually cracks, can be essentially extracted. And we actually took an approach, what's called a multi-unit approach, which is actually leveraged from medical imaging, that allows you to actually take the input data, decompose them into 3D geometry, into surface normals, and also cracks. And this actually effectively is the pipeline. Since we don't have, in the early part of the project, the data, we did everything in simulation. So you can start actually with simulation data, and then you can actually, effectively you start with a model of the world, and then you simulate the world, and then you can actually use the simulated data to train this multimodal architecture, and then you can actually then test it with data. So that's basically how we did this. And here you can see essentially this crack generator generating these cracks. And then the next slide will show you basically how we take that data and then we can produce, all kinds of things like graffiti, moss, and other types of defects so that you can actually sort of simulate reality using actually a whole range of perturbations. And then you can use those data set along with the architecture that the human provides to be able to then take this input data and then separate them into cracks, surface normals, and then depth variation. And what we have shown in the pilot is that this actually works. We'll show you in the later that this actually method works with the tunnels. One of the key requirements is that the simulation has to be close enough to real in order for the simulation to transfer to real. And this is a well-known issue. And so therefore, the whole issue is how to bring simulation models close to real and so on. And here you see actually results from other data sets which show that this technique works. And then we also did the same for simulation of steel bridges and corrosion seals. So again, the idea is that you think about actually a material and the material degrades and there is a physical process and we can actually model the degradations. And you can use now modern tools, graphics tools, to be able to simulate these type of material patterns and then to be able to essentially train a variety and generate a variety of examples from which you can actually then train a classifier, which then can be used on real data. Here you can see that the corrosion part of the scene is sort of highlighted as the dominant ones. And you can see it is not absolutely perfect because you need actually further real data and real training to augment it. But nevertheless, the concept is validated. And this also has been validated with the concrete data, with the exposed bars and corrosion. And the other aspect that is basically new here, essentially, is that we also have the 3D geometry. So we can directly process the 3D geometry and try to use information to get back, especially the surface variations. And that also can help you in actually classifying. So we've actually adapted that here, and we've used it in the typical applications which involve taking this image at a distance of 2-3 meters. This is not necessarily useful, but when you go closer, it can be useful. And this is actually the result that we got from the Turin pilot data. So you can see the actual tunnel data and then the kinds of hypotheses and results we get. We also have a user interaction that can go on where you can actually allow a user to mask off some things that they don't want or to select and reinforce some points. And here are some examples of these different modules working in the Turin dataset. And you can see here, this is the topology piece getting a lot of hypotheses. And this is that multi-unit simulated based training method, which also does a good job in extracting the crack hypotheses. And then when you can fuse it, you can get actually a pretty good estimation. Similarly, you can do the same on the other data sets. So this is also showing that there are some, these methods are actually already doing their job, and a combination of them helps you in improving. The exact nature of how to combine is actually further work to be done, which is actually depends largely on large amount of data and actually integrated training. So that is, we already have the process for that. And you can see here clearly the combination of these things that allows you to make progress. I'm only showing the, I didn't show the human interaction piece, but you can guess how that works. So in a sense, what I want to summarize is that we have confirmed that our systems engineering methodology works, and it has a flexibility to build a portfolio of algorithms and combinations for a range of visual inspection tasks. So that's basically one major finding. The other thing is that we could actually show the use of simulations to transfer to real. And we also showed that there are some limitations, but the limitations are already explained by design. Therefore, we don't have surprises anyway. And then the key point is that a human integration into the loop properly and then integrating that would be a major step towards commercializing this type of solution into practice. Thank you.
Thank you. Thank you, Ramesh, for this presentation. So now we welcome as well our colleague from Forte, Manolis, who you presented virtually as well. Ramesh, the floor is yours.
Hello, can you hear me now? Okay, let me share my screen. Good morning, everyone. Okay, can you see my screen?
Yes, perfect. Thanks.
Okay, thank you. So, good morning, everyone. My name is Manolis Michailodimitrakis, and I am from Forth, and I will be presenting the Redcom. So, what is the Redcom? Redcom stands for Rapid Emergency Deployment Mobile Communication Infrastructure. The main objective is to build an infrastructure to support and handle communications in emergency situations where standard communications networks are not available. For example, if we have an earthquake and we need to conduct inspections on a bridge or a tunnel, we need to have a communication infrastructure that can provide means for involved parties to communicate. This communication can be internet access, radio access, or cellular coverage. So what we did was to build a trailer that we can move around and put in this trailer equipment necessary for the communications. So first of all, how do we power the Redcom? The Redcom power supply is provided by an inverter. This inverter has 4 available options. First, of course, is the external power. Second is a petrol generator. Third is a wind turbine. And fourth are solar panels. The solar panels and the wind turbine charge 2 batteries that are connected with the inverter. The inverter, the batteries, and the generator are inside the Redcom trailer. The wind turbine and the solar panels are mounted externally on the trailer. Regarding the network deployment of the Redcom, we have 3 options for Ethernet access. We have an LTE modem, which uses SIM cards to provide Ethernet through cellular data. We have satellite modem to provide Ethernet through satellite. And also we have several access points that can be used as clients to receive Ethernet access wirelessly from another wireless station. Of course, there is also the obvious option to plug in a cable. Additionally, on top of the Redcom, we have an IP camera that we can use to view from a higher ground and also a GSM base station that can provide cellular coverage to mobile phones in the nearby area. The access points, the camera and the GSM base station are mounted in a mast that can reach 9 meters height. This mast is retractable for easier transportation. Inside the Redcom trailer, we have installed a server powerful enough to host all the Resist platform. This server uses the Hyper-V as a hypervisor, and all the Resist components are installed in virtual machines in this server. Having all this inside the Redcom offers faster transfer speeds. Additionally, having all the virtual machines enables the use of a global intrusion detection system. The Redcom has 2 compartments. In the first compartment, we have the inverter, the generator, and the charges from the wind turbine and the solar panel. In the second compartment, we have a rack, and inside the rack, we have the server, the monitor, the modem, the router, and the switch that are all connected with. How the Redcom fits with the rest of the Resist components. As I have already mentioned, the server with all the virtual machines that run the rest of the components is inside the Redcom trailer. The drone, the ground station, etc. are in direct communication with the server via the Redcom. This is how the Redcom looks like. And this is the end of my presentation.
Is that-
I will do it. Announce the next presenter. I will do it. I will do it. Can you put on
Thanks, Manuel. Now you have our colleagues from European Dynamic who you present.
No.
Okay. Hello.
You take it. Yes, yes.
You have to show this on the screen.
Yes, I can do. Oops.
Okay. Should be this one.
Just a minute.
Okay. So hello from my side. Anastasia Garbi from European Dynamics. I'm going to present the integrated degradation activities and the integrated platform. So, okay. So this is a very complex figure, but it shows how the simple graphic presentation of the whole system that Margarita has presented at the beginning has actually materialized. I will not go into detail, but I want to indicate some major parts of this architecture. So first we have this left side, that is, we call it the data providing components. So we have fixed sensors that are monitoring infrastructures on site. And then we have the sensors that you have seen here before, the presentations, that are mounted on the drone, and they are collecting data on the field during an actual inspection. And these are then processed by the analytics algorithms that you have seen, and they are stored and manipulated by the total station and the SGS that controls the robot and the drone and the processor on the field. All these data are then transferred to the SDSS platform that is actually working as a data broker application, a data broker platform that is actually has the role to get all this data collected and provide homogenized, let's say, by storing them in a common format, and then providing it to the applications that are actually using it for the processing and the decision making. And then here we have some applications for visualizing this data, the photogrammetric visualization, the structural vulnerability and risk assessment that uses the knowledge and the designs of the infrastructures and monitors actually the progress and the development, let's say, of the problems that appear on the infrastructure, and then the mobility continuity that takes its own data from the traffic and the mobile application with interaction from with the drivers in order to guide the drivers on the road and any alternative routes or issues that appear. And then we have the cybersecurity platform that ensures that all this system is secured and is not possible to hack. I would like to give a short overview of this integrated environment that we use. This is an existing platform, that open source platform that has been developed by European Dynamics, and it provides, let's say, a web 2.0, a modern application environment, which allows to integrate heterogeneous applications, like in this case. It has been customized to support the operational requirements of the Resist platform and implement this architecture. It actually features a web desktop that simulates a desktop environment on the web, but provides an easy access to a terminal machine, which provides single sign-on and role-based access to all these applications that are integrated. In addition, it ensures data integration by collaborating with this STSS platform that we have seen before, that provides this common data model. And then it enables full customization to the needs of the project, of the environment, and allows easy integration in different ways of all the potential various applications. And actually, this is doing on the fly without removing the system from the online running and production stage. This is the screenshot from the application, from the actual application. So that you can see here is admin environment where you, I'm sorry, this is the process management environment where you can see what are your tasks. I will show you some ideas about this implementation later. Here you can see what is going on with the instances of the processes that are running. Here you can see the photogrammetric replication of, here is, I think, the tunnel, the mobility continuity module, and here are the data, access to the data that has been collected in the platform. The whole process of the inspection has been detailed in a very detailed workflow, as you see here, that includes all the operators that are involved. For example, the control center operator who initiates the inspection because he sees a need to go to a specific place. The Rpas operator who has to manage locally the Rpas. The user of the computing vision system, and all the other players that are involved, and there is a specific workflow that is followed. There are two versions of the inspection process. This one is the complex, let's say the most detailed, more detailed and more that includes all the components. That is the process that takes place when there is an identified point of interest in the infrastructure, and this has to be further evaluated with using all the components of the system. And then there is a quick inspection process that is used in order to identify initially the points of interest. So a drone is just sent to a mission to monitor the infrastructure, let's say from high level, and identify the areas of interest. And here, this again, you cannot see in detail, but it represents the workflow actually implemented in the system with the various roles of the users involved. And this is actually executed during the mission. And every actor gets informed when he needs to perform a task. So yeah, that summarizes the integrated environment. Thank you.
Thank you, Anastasia, for this presentation. So now we will have our coffee break and you reconvene at 10:50. Okay, thank you. See you in Hello again to all. We will restart, we continue the meeting. So now we'll have the presentation from our colleagues from ERA. Dimitrios will manage it virtually. Thanks, Dimitrios. The floor is yours.
Thank you. May I share my screen?
Yes, you have access, please.
Can you see the full slide of the presentation?
Yes, it's fine for us.
Okay, thank you. I'm Dimitrios Bilionis from the Environmental Reliability and Risk Analysis, and I'm going to talk on the time-dependent degradation of bridge and tunnels materials. The objectives of this task were to develop time-dependent material degradation models for concrete and steel bridges or tunnels exposed to aging and climate change that will provide structural analysis with time-dependent quantitative input or loss of steel thickness due to corrosion. Will also assess the impact of climate change on material degradation and provide a map of estimated defects that will be used in subsequent remote pilot aircraft system or Rpas measurements to assess the evolution of these defects. The Rpas input to the modules on material deterioration will include location, width, and depth of cracks in steel and concrete members, location, size of spalt areas in concrete members, location of exposed steel bars in concrete members, and location and size of corroded areas in steel members. The modules on the material deterioration will provide the structural assessment with the location and magnitude of rebar section loss in concrete members or the location and magnitude of metal section loss in steel members. This is the flow diagram of the process. On the top is the input by the Rpas system, which measures various defects or cracks on concrete bridges or steel bridges and tunnels. The output of the Rpas system provides input to the material degradation models, and then based on the evaluation of the output of the material degradation models, we can perform the structural analysis and estimate the structural condition, the effect of damage, and the safety of our structure. Regarding the corrosion degradation of structural steel, the estimation is exclusively based on Rpas measurements of corrosion depth. A proposed equation for estimating the depth of corrosion is presented in this slide. As we can see, the depth of corrosion is a function of the time of the exposure and some other experimentally derived constants that are usually available in the literature. Now, regarding the impact of climate change on the corrosion of structural steel, there are some models presented there are some models proposed in the literature. The first model evaluates the effect of sulfur dioxide in combination with temperature and relative humidity. So we can see that the total loss of thickness is a function of the concentration of sulfur dioxides, the relative humidity, and the temperature, and some other values. And we have applied this model for some scenarios of various values of sulfur dioxide concentration, relative humidity, and temperature. And the findings show that there is a negative temperature effect in the interval between 10 degrees Celsius and 21 degrees Celsius. The relative humidity affects the corrosion, and also the level of sulfur dioxide significantly affects the corrosion. However, we should keep in mind that in Europe, over the period between 1988 and 2008, the annual mean sulfur dioxide concentration have decreased from 30 micrograms per cubic meter to 2 micrograms per cubic meter. A second model that evaluates the effect of chloride in combination with temperature and relative humidity is proposed in the literature. The difference between from the first model is that in this equation we should also take into account the chloride deposition, and but we should keep in mind that the chloride herein refers to salinity from seawater and does not include other possible sources, and also according to predictions, the chloride deposition is not expected to change dramatically in the future. The application of the second model in similar scenarios of sulfur dioxide concentration, relative humidity, and temperature shows that the expected increase of 2 degrees Celsius in temperature can have a significant negative impact on steel corrosion in environments with a high chloride concentration. This is evident if we look at the numbers and see that for huge chloride concentration, we have a greater increase in corrosion rate due to increased temperature. Both models can be adjusted to the location of interest based on measurements from the computer vision system on the extent and depth of corrosion damage and the ground penetration radars on the depth of corrosion damage. Regarding the corrosion of rebars in reinforced concrete, there is a number of models proposed in the literature, such as the one by Andrade et al. And according to that model, the crud width at time t is a function of the corrosion penetration, the concrete cover, and the original rebar diameter. Furthermore, as we said, there are a lot of models proposed. We can say that the Rpas system can be used in order, based on its measurements, in order to select the most appropriate model that can fit in our case. Regarding the impact of climate change on the corrosion of reinforcing steel bands, and as focus on the carbonation index, there is a number of papers published in the literature, and the majority of almost all papers predict that the estimated value of carbonation depth by years 2100 will increase by around 40 to 45%. Now, if we consider the chloride concentration, then we can see that there is also research published on this topic. However, there is no consensus regarding the increase in the value of chlorine in use depth by year 2100. However, we should point out that all studies show that the effect of climate change on the reinforced concrete structures affected by chlorination-induced corrosion is lower than in the case of carbonation, but it is still considerable. Regarding the impact of climate change in the presence of both chlorination and carbonation, to our knowledge, there are no studies that evaluate that impact in the presence of both carbonation and chlorination. So to conclude, we should say that there is a need for accurate mathematical models accounting for the effects of climate change, and specifically the change in temperature, relative humidity, and carbon dioxide levels on material degradation. And based on the results of RESIST projects, we found that the expected increase of 2 degrees Celsius in temperature can have a significant negative impact on steel corrosion only in environments with a high chloride concentration. Thank you.
Thank you, Dimitris, for your presentation. Now we will welcome our colleague for DBA to present the structural model in condition analysis.
Yes, but they have to change the share window. Is it okay? Just 1 second, please. Here one.
Hello, I'm Parasiris Apostolos from Dimitris Bayraktaris and Associates. We make the structural assessment tool. Yes. How is it changing the slide? Okay. We have created a lot of tools and we're starting from material tools. Regarding the constitutive loss of materials, reinforced in steel with hardening branch from, as we see on the right side, with constitutive models. For concrete, compressive branch and tensile branch until the ultimate stage. The constitutive law for the stress transfer at the interaction surface between the reinforcement and the concrete due to friction and mechanical interaction, as we see is introduced through this modeling. Also, we have take account of time effects on concrete regarding the strength related to age, the compressive strength of concrete related to age, the creep, through the creep coefficients for the permanent loads applied, that takes account relative humidity and the perimeter in the contact with atmosphere. Also, the string cuts, the autogenous and the drying string cuts are also taken account. We have implemented tools for temperature effects regarding the changes on the properties of materials on high temperatures for cases of fire. And the main tools that we have implemented is from the one hand, the local condition assessment, and from the other hand, the global. I'm sorry, can you hear me? Okay. The local condition assessment and the global condition assessment. What are the measurements that are needed? At the visible internal perimeter of the tunnel's cross-section, we need to have cracks geometrical measurements regarding the width, the depth, the multitude, if we have a multi-crack, and if we have a multiple crack, we need the spacing. We also need the crack's location. For a slide, for a constant distance along the axis of the tunnel, we need the XZ of the crack. Also, for the global condition assessment, we need the deformed shape of the perimeter and the resulting convergences at 6 pairs of characteristics points with respect to the initial and undeformed shape. Here we see a crack image, what we say about width, what we call width, depth, and on the right side, we see multiple cracks and the spacings between them. For the local condition assessment, we make the assumption for linear distribution of strains along the cross-section, and so the strains of concrete at the upper and the lower planes are related with the strains on the reinforcement steel through the curvature and the axial strain. Now, according to the theory of Dr. Dimitris Bayraktaris, through the width crack, it is estimated the strain on the steel. Down we see the diagram at the point of the crack where the concrete does not take any strains, but has only the residual strains after the ultimate state, and all the strains are taken through the reinforcement steel. From this point, the curvature and the axial strain are calculated. After we have the axial strain calculated and the curvature, we are able to calculate the internal forces, the safety factor, and the stiffness factor, given the crack geometrical characteristics and the position of the cracks. After this stage, we go to the global condition assessment, and here we see that all the cross-section is separated in 36 parts. The calculation of the soil pressures and the internal forces, axial force, shear force, and bending moment along the perimeter of the tunnel is based on convergence measurements along six chords. The 6 chords, we will see them on the next slide. The load cases are linearly distributed. The self-weight, the ballast load, and the shrinkage. Here we see the chords. The chords are calculated for the initial undeformed geometry and for the deformed geometry. Through the convergence between the chords of the undeformed and the deformed geometry, a system of equations is formulated for unified pressures. Through this system, we have the solutions that we mentioned previously for the global condition assessment. And this is all the process. The results of this process, we can see in the integrated platform. Thank you.
So we have a question on the chat. Dimitrios, could you please help us on this question?
Yes, it is a very interesting question. However, to be honest, I cannot answer that on this time because I have not performed the corresponding literature research because I entered the project at a late stage. But I can pass the question to my colleagues and get back to you with more information. And now I would like to ask if I can make the second presentation since Dr. Matafrodistou could not join us today. It's regarding the risk assessment management.
Yes, perfect. Just to point, Jesus or audience, you receive this information, will keep it in mind to reply you your question. Okay, Dimitrios, the floor is yours.
Okay, thank you very much. So, can you see the full slide? Hello, can you hear me and see the full slide of my presentation?
Yes.
Okay,
yes.
Thank you. So I'm making this presentation on behalf of Matafrodistou from Marisa. And so if you have any questions, of course, you can tell me and I will pass all the questions to her. She can join us today. And the presentation is about risk assessment and management of critical highway structure under extreme events. The objectives of this task was to develop a methodology and a tool for risk assessment and management for critical land transport structures under extreme events in order to optimize the selection of preventive and reactive adaptation measures and to implement the above methodology in the case of highway bridges and tunnels. The risk management can help us in deciding whether a protection and adaptation measure should be implemented or not, and the final decision is based on its cost effectiveness. If after performing some risk analysis and cost analysis, we found that the measure is cost effective, then we can implement that measure. If not, then we should not implement the measure and do nothing, so leave the structure as it is. Of course, it is obvious that a hazard event will affect our structure, which in this case might be a highway, bridge, or tunnel, and can cause damage or loss of function. Any damage or loss of function can have social, economic, and environmental consequences. Especially for social and economic consequences, we may have direct impact or indirect impacts on the structure, the operator of the structure, and the society. The hazards under study are earthquakes, explosions, fire, landslides, scouring of the river-bedded floods, high winds, and cyber attacks. We should mention that all the above have been studied in tandem with adverse climatic conditions that may accelerate material degradation. The first pilot of our project was the Egnatia Motorways Bridge T9 in northern Greece. For this bridge, we have estimated the monetary consequences of damage without protection measures, and we have also used two scenarios. The first, according to the first scenarios, an incident happens when there is the average number of vehicles on the bridge at the time of incident, and based on our calculations, in that case, the total direct cost will be around 20.5 million euros, while the total indirect cost will be much higher and will be close to 20.25 billion euros. In the second scenario, the same incident happens when the maximum number of vehicles are on the bridge at the time of the incident, and while the total direct cost is the same with the previous scenario, the total indirect cost is slightly higher as expected. So, if we consider as protection measures the strengthening of water pumping, water drainage works at the eastern abutment by a new drainage tunnel and new water wells for pumping underground water, and a measure which is will cost around 5 million euros, and considering that our incident is an earthquake with probability of occurrence equal to 0.009 as the extreme event, we can calculate the break even. But we should say that if we consider only direct cost, the measure is not going to be cost effective, since the break even gave us a probability of 0.40, which is higher than the probability of occurrence of the event. However, if we consider total cost, so we include in our analysis the indirect cost, the measure will be cost effective, since the resulting break even is 0.002. Furthermore, we have applied the second scenario, and we have tried to estimate the benefit from the use of Rpas in the inspection and integrated assessment. And in this scenario, we assume the average number of vehicles on the bridge at the time of the incident. And according to the calculations for direct and indirect cost, we can find that the incorporation of Rpas may save approximately 125 million euros. The second pilot of the RESIS project was the St. Petronilla tunnel in Italy. For this structure, we have simulated an event of fire with duration of 2 hours. In this graph, you can see the bending moments inside the tunnel. And we have performed the cost-benefit analysis, and we found that the resultant cost in the case with protection measures is higher than in the case with no measures. So it's slightly higher by around 500 euros. So the protection measure will not add anything, and we can say that there is no need to implement it. And the third pilot was the Milores viaduct on motorway A32 in Italy. If in this case, if we perform an analysis where for this table is for no protection measure, and the cost of if average number of vehicles are on the bridge at the time of incident is around 18.7 million euros, the total direct cost. And in case we apply protection measures, we can see that the total direct cost is around a third as compared to no protections, and it is close to 6 million euros. Thus, we can estimate that the break-even is around 0.32. And if we consider, as in our case, we consider an earthquake happening concurrently with high winds and a heavy truck in the middle of a bridge with a probability of occurrence less than 0.1, the protection measure is not cost effective since it gives break-even higher than 0.1. So to conclude, we can say that the duration of reinstatement of operability dramatically affects indirect costs. Based on direct cost alone, proactive strengthening may not be cost effective regarding extreme events. However, indirect costs and specifically travel delay costs to the road users can be a multiple of direct costs. And based on total cost, including indirect cost, proactive strengthening may be cost effective regarding extreme events. So it is evident that if you incorporate indirect costs in your analysis, you may get a different result than if we limit your analysis only on direct cost. So indirect costs are important. And finally, robotic inspection can make a significant contribution to both direct and indirect costs. However, in this methodology, there are some challenges which are due to the data gaps that there exist regarding the construction costs, the construction duration, pace of restoration and reinstatement of bearability, cost of travel time, fatality cost, and use of bridge tunnels. So the more data you have regarding these aspects, the better models and predictions you may and decisions you may make. Thank you very much.
Thank you very much, Dimitris, for your presentation. So now you are moving for the next one. Is your colleague from STS. The floor is yours, Yazan.
Hello, everyone. Let me share my screen. Do you see my screen now?
Yes, it's fine, thanks.
Perfect. So hello, everyone. I'm Iason Soumarakis. I work as a security engineer in Sphinx Technology Solutions, and we were responsible for the cybersecurity framework in Resist. So the cybersecurity framework consists basically of two key components. The cybersecurity controls that are responsible for identifying, mitigating, and preventing cyber threats, and the cybersecurity assurance mechanisms that are responsible for reactively and proactively identifying cyber threats. The cybersecurity controls include typically the intrusion detection system that is responsible for identifying attacks in the network level, include authentication and authorization of users, for instance, for our universal interface, cryptographic mechanisms that are used to protect and encrypt the communications, for instance, between the Rpas and the ground control station, or between calls back to our backend. And finally, resilient communications that are supported by Redcom via the redundant channels. Next, the cybersecurity mechanisms involve three types of assessments in Resist: direct and indirect vulnerability assessment. That's how we identify if a software component, for example, is vulnerable to publicly available vulnerabilities. We have penetration testing assessment that tackles this vulnerability and actually checks with the system if it's indeed vulnerable. And we have the continuous monitoring assessment that is responsible for monitoring key aspects of specific and important assets, for example, the intrusion detection system, to make sure that they are up and running. If you can see on this figure, this is the network architecture of Resist. I'm going to place some of these components in this figure so you can take an indication on where they are placed. For example, the intrusion detection system is placed on the backend level. We have a resilient communication across all types of communications in Resist available through Redcom. We have cryptographic operations in most of these communications, especially between the ground control station and the Rpas, or between the Redcom and the backend. We have authentication and authorization in our universal login page, and we have continuous monitoring various services such as the systems running on the backend or even the security controls. These are just indicative placements. There are many more in place actually. So now a few screens of these controls, of the cybersecurity controls. Specifically for the intrusion detection, we are using Cloud IDS. That's an implementation provided by Forth and is responsible on identifying attacks on a network level that originate from outside Resist safe intranet, but also originating from internally. If, for example, an internal VM is compromised and tries to attack other VMs, other systems of Resist. The IDS is deployed on a hypervisor level to have an overview of all other subsystems deployed there, and it also enables statistics about the attacks, as you can see on the figure, such as the sources of the attacks, the type of the attack, and how many of these exist. Next, we have the Early Warning Intrusion System, EWS. That's basically a honeypot that is responsible to appear such a vulnerable service so that attackers try to exploit it, so we can get some interesting insights and threads about the attackers, such as the country that the specific attacker is executing their attack from, the ports, the network ports that they are targeting, or even the type of traffic that is coming, UDP or TCP. These are just two indications of the security controls. And moving on to security assurance, I'm going to show you the graphical user interface that the cybersecurity admin can use to initiate and assess the security posture in Resist. The main view is this one that provides an overview of Resist platform. As you can see, this is an asset overview view. So you can see the types of assets that are available in Resist. These are the assets that we included to be assessed to make sure that these assets are secure and protected. So this view gives you some quick graphs and overview of this. The next view provides the extensive list for these assets and some means to add new assets. And then on the most important part of this environment is the assessment, the assessment view. On this part of the graphical user interface, the user can manage and execute security assessments. The three types of security assessments that I earlier explained can be initiated from here. On the figure on the right, you can see two types of assessments that are displayed: the OpenVAS assessment and MVD's vulnerabilities assessment. From this view, the user can navigate on in these assessments, but they can also start a new one. If they navigate into a specific assessment, for each type of assessment, there is a specific view tailored to that assessment. For this vulnerabilities assessment, the first thing that the user sees are some key important indicators. For example, out of the results that the assessment identified, in which categories, what's the categorization of them? So the vulnerabilities assessment has 3 types of categorizations: low, medium, and high. So on the figure on the right, you can see a graph indicating the numbers for this type of categorization. Or on the figure on the right, you can see the most vulnerable assets based on how many results were found for each asset. In this example, the HTTP server and Tomcat were actually the most vulnerable assets. But you can also see a list of all the results found for this type of assessments with specific details for each result, such as which asset it was tested, which security property was tested, and more results can be also viewed if we open each of these, if we expand each of the results, and this is specifically for each type of assessment. So for example, vulnerability analysis provides information based on the common vulnerability enumeration standard. So as you can see here, this maps exactly on this type of standard, and you can the security admin can see information such as the CVE identification, the attack vector, complexity of the attack, everything as defined by the CVE. Penetration testing is a bit different because it depends on the tool that is used to provide to generate the results. So in this case that we're using OpenVAS, the results are mapped to what OpenVAS can provide. And in this case, it gives you an extra technical flavor on what is this vulnerability, how can be exploited if possible, and how can be mitigated if possible. Finally, we have the results for continuous monitoring. That's also very specific results depending on the monitoring rule. In this instance, we are trying to make sure that the asset is available at all times. So if a violation is found, we get an alert that, you know what, the asset is down, you should take a look at it. And this basically concludes my presentation. Thank you. If you have any questions.
Thank you,
I cannot hear you.
Yes. So no, from the moment we don't have any question. Thank you once again for your contribution.
Thank you.
Now we move to the next presentation. It will be our colleague who will manage online, Todoris from ICCS. Todoris, the floor is yours.
Okay, thank you. I'll share my screen. Can you see my screen?
Yes, it's fine for us. Thanks.
Okay. So in this presentation, I will go through some of the basic functionalities of the mobility continuity app, which has been developed also for the Torino use case. We will look into the basic components and also have a more detailed view on the actual look and feel of the mobile application that has been developed. The basic components of the mobility continuity application is a simulation for urban mobility component, which actually enables to provide analysis regarding the actual the traffic, which is estimated along a part, let's say, of a highway, thus providing insight regarding parameters such as average velocities and road occupancy. So within the context of the mobility continuity app, we have used this application to extract information regarding the average velocity given a closure of a lane along the test site. Another big component of this application is the Open Trip Planner. The Open Trip Planner enables getting itineraries that can take a passenger from, let's say, point A to point B through various modes of transport. In this case, we have enabled transport through a car, and there's also another component which is used within the app, the behavioral analysis component, which is has been developed by our partners BGU, and which enables analyzing the commuter characteristics in order to provide them more detailed messages and a more personalized experience. Along with these components, we also have another, let's say, component which actually functions based on Twitter messages. So we have the sentiment analysis tools, that we call it within Resist, which let's say tries to analyze Twitter messages and extract the actual state of emotions that from those messages. These emotions are, let's say, some 8 basic emotions such as anger, anticipation, disgust, fear, joy, sadness, surprise, and trust. And these can be used alongside the mobility continuity application in order to assess and evaluate the overall status within a given area, and thus provide the operators and road operators also a more detailed view regarding driver behavior. So regarding the mobile app, okay, we have developed the main functionalities such as the registration and login, and this is the screens that you see here. Also, we have a questionnaire which can be filled in by users once they first log in within the application, and within that questionnaire, we make some basic questions that enable us to do the behavioral analysis as developed by BGU. This functionality has been integrated within the app, and what basically happens is that based on this questionnaire, we can deduce 3 basic classes of, let's say, road of drivers that need support, drivers that would like support, and drivers which are in general cool and which can also receive support. The basic difference between these, let's say, 3 classes is that for the 2 classes, we have to be really careful regarding the way that we show messages. We cannot show messages while driving, whereas for the more experienced and the cool drivers, we can also provide some messages while on the move. Regarding the trip planning functionalities, what we have included is trip planning based on car. Of course, we can easily integrate other modes of transport, as we have done for the Ignatia case. And what is also included within the app is the possibility of deviated from Petronilla tunnel in case of a hazard. So this is what you see in the rightmost image that you can see here. Also, one really basic functionality is that when the application goes into the navigation mode, the drivers can receive notifications regarding road events with options to reroute. So in this case, if a user presses the button, he can get a new recommendation because there's the possibility that the route that he has taken is no longer a possibility due to some event, some road closure event. Also, we have notifications regarding lane closure. So as you can see here, we have an event of lane closure, which along the same Petronilla tunnel, which notifies drivers about the actual closure, and also based on the simulation of urban mobility, we have an estimate regarding the average speed on the lane, which is let's say which is a result that is based on inputs that we provide through the dashboard, the operator dashboard that you see here. So what we have is the operator dashboard, and the operator dashboard then enables the road operators to either activate an event on a given region, or also provide some basic inputs for the simulation of mobility, such as the amount of, let's say, traffic in the sense of vehicles per hours, and the amount of heavy vehicles occupying the road, in order to get an estimate regarding the average functionality, which average velocity along a route, which is also notified to the users through the mobile app that I saw before. Sorry. Also, we get an estimate of the average velocity of a closed to open lane ratio for the operators, in order to also have another metric of how much lane closure has affected the overall, let's say, traffic on the road. I will try to show you also, let's say, a small demo of this functionality through an emulator of the app. So, for example, what you see here, the blue dot is emulated position of a journey start, which is normally provided through GPS. So users can also put in the text box a destination. So in this case, we have selected Susa. Sorry again. So this is what we get as a recommendation of the trip through the said Petronilla tunnel. In normal situations, we also have the steps, the actual itinerary within the app, let's say the recommendation and the time of the trip and the distance. And we can go into the, here we see the itinerary on the map, and we can go into a navigation mode. So in the navigation mode, the application waits for an event. So now I go to the dashboard and apply an event through the dashboard. So we see we have actually closed the road, and what we wait for is this, what we expect as users to receive this message that they received here, where we can see that there is some incident, and we can see now that there is a new itinerary for the actual trip, which bypasses the incident through an alternative route. And this is the part of the app that covers, let's say, the basic trip rerouting. So this is pretty much from me. Thank you very much for your attention. If you have any questions, let me know.
Thank you to Doris for this presentation. So now we have the overview of pilot area, scenarios and demonstration, and this will be managed by our colleague Saverio from Tecnosita.
Sapete quelli qui che sono senza occhiali? This one? Ok, e poi c'è il video dopo che... Sì, ma quello lo richiami da dentro. E così. Aspetta, se devo mettere le mani. Ok, this one.
Okay. Thank you to everybody for being here. For this project, Tecnosita had the fortune to have a huge tunnel ready for tests. The tunnel was built about 1992 starting works and 1995 end of building works.
Sorry for the interruption, because the online participants cannot see your presentation. Just one moment.
Okay.
Adesso la connessione. Dove ci fosse la condivisione? Okay.
Yes.
Perfect.
Okay. As I told before, we had the opportunity to put for this project a disposal of a tunnel that is a safe exit for a longer double-way tunnel from Susa to Bussoleno. The tunnels are long about 5 kilometers. And the Santa Petronilla tunnel is a security way for evacuation in case of fires and huge accident in the main tunnels. This tunnel is close to traffic, so we always use it for experiments, to run tests, whatever, in a safe place to run every kind of tests. Sorry. Okay. The tunnel is halfway from Turin to France, near the town of Susa, and is a two-way tunnel for traffic, as you can see. This is the pilot in which we test drones flying without GPS or GNS signals. And the tunnel is long about 500 meters, and it is connected to a fire-safe door to the main traffic tunnel. There is also a ventilation central to provide fresh air in case of fires in the main tunnel. In this tunnel, we did all connection for networking. We had installed the Wi-Fi networking. We tested Wi-Fi motion connection at speed traffic. And also we have the SCADA and the connection system for the motorway. Now I left the speech to my colleague Walter for technical aspects of the test pilot. Thank you very much.
Thank you, everybody. I'm Walter from Tecnosita. Yes, Saverio has explained how where the test site is in the tunnel, how is composed. But I want to give you the position of our view as a maintainer and a road manager, because what this kind of tests and the result of this project will bring to our experience, to the experience of the road manager. Let's start beginning. As you can see in the previous presentations, the cost of both the social and monetary cost, economical cost of some critical events is very high. So security is the main issue of a road manager of the road and the tunnel. security is not only during the event, but also before and after the event. So start thinking what happens if a serious event occurs in the tunnel. We start with the alarm management. We have, as Saverio told, a lot of sensors, SCADA, TVCC system that will help us to identify the event in the very early moments. After, we need some procedure and some emergency plan to manage the traffic, avoiding more traffic coming inside of the tunnel and coming to getting the things worse. So during the serious event, the main issue is security for the life of the people. Second point is the life of the infrastructure. Of course, during the general, I can say in English, okay, during the emergency plan testings, you have also to manage the dissemination of of what are happening to the general police authority and every actors involved in the system. Of course, in the end, you have the rescue team intervention. In the end, I mean, after maximum 2 minutes. This is the main time that we need to intervene. I'm speaking about procedures and emergency plan because the procedure and the emergency plan is what you want to have to respond in a fast way. So you need to be trained to manage the request of emergency, to inform the police, the fire brigade, and all the main actors involved in the management of the emergency. And also people that are working near the infrastructure, or for example, for the manager of the road, needs to be trained to manage the emergency. But the procedures and the emergency plan is only for the trained people. I mean, emergency teams, professional operator, but also the user must be involved in the correct way, because a lot of bad incidents inside of the tunnel have a problem with the user. So what we have simulation of a worst case in totally the fire inside of the tunnel. We have thinking how we can use the result of a project like Resist to improve the emergency plan. For example, during the emergency, you can give some application to the user to just ask for help. As you see, something is happening, and this is the main control room video that is shown that the operator can manage the rerouting. In this case, they are putting some information in the variable message sign along the motorway. They are able to receive the information from the application of from the user cell phone, but thinks that inside of the tunnel there is no cell phone signal, so they can use the Wi-Fi inside of the tunnel to communicate in case of the emergency. This is some simulation of what can be done by an operator. And of course, when everything is done, he can control what are the situation in the tunnel, or just rerouting as shown in the video, rerouting the traffic. But we are speaking now about, okay, we have saved the life, no problem, good. But after, what can be done in a situation where a fire have ruined the tunnel infrastructure, as we have shown, has some presentation before shown? We can think about using the, communication enhancement we have seen that can be used during the event. But for example, after, in a very dangerous environment like a just like a tunnel that have a big fire inside. It's very difficult to reach the place to make visual inspection or to make instrumental measurements. So one idea can be used also, the idea of drones, of new inspection shown by Resist, to add it in an after inspection also, not only in the preventive inspection. Of course, predictive maintenance can bring a better quality of the diagnosis and the status of the infrastructure. This will bring for sure a better maintenance program, longer life of the infrastructure, and a better life of also the people that use that infrastructure. I think also another big point is that when you are making tests in the infrastructure, like concrete infrastructure, or we have seen also steel infrastructure, sometimes you need to make destructive tests, to make drills, to be sure about what happens under the surface or behind the surface. With all the ideas and demonstration that the previous presentation shows, can be in these destructive tests can be reduced maybe, and so that will bring a longer life, better maintenance, and for sure increased security, because the security is made by before the accident, during the accident, and after the accident. This is what can really matter as the idea that we have shown today, what can be really used and matter for a road user and a road manager. And I think we can now move to see some drones. Thank you.
Thank you, Walter. Thank you, Saverio. Let me also thank the whole technical staff team for their preparation of this workshop and the pilot, and for their hospitality as well. As we are still on time, and this is not quite typical in such workshops, I'll ask you to be patient and maybe watch another 10 minutes, let's say, video we have prepared before the lunch break. I think it will be really interesting to present to you, let's say, a detailed inspection process through Resist system. Okay, I think, okay, let me share the screen so also the online participants can see the presentation.
This is the full screen.
No.
That one.
It's not presented in the
But
meeting.
I think that.
Yep.
You have to choose.
Yep. Okay. So now everyone can see the screen. Put it. Okay, great. So let's say that we have a process for a detailed inspection of the infrastructure. Now we'll present you a scenario. This is the sequence flow that will be followed through Resist. So let me take a brief, let's say, description. So we have the cybersecurity assessment that is a continuous process and happens all the time. So let's assume that we have an alarm or an alert about an event. Maybe this could be an earthquake that may affect the infrastructure, or an incident, an accident, a crash or something that also may affect the infrastructure. So in this case, this alarm is received by the traffic control center that Saverio presented before, and also by the mobility continuity app through the Resist platform. So in this case, a detailed inspection process will be initiated. The drone missions will be prepared and will performed. We will collect some raw images and create a 3D point cloud and process also these images in order to assess them. And in case that we have some findings, some defects or something in the infrastructure, a new mission will be, let's say, initiated for further measurements, ultrasonic measurements and so on, to check the status of the infrastructure. Based on these measurements, the structural vulnerability and risk assessment will be performed. And when everything is okay, is checked, it's back to normal, we can reopen the road. So let's start with this flow with some videos on how resist reacts in such systems. So this is the cybersecurity assessment. Okay, you can see the login to the platform, and now we will connect to the cybersecurity module. Okay, you can see here. You can select the organization, the project, or the asset we are talking about. We select pilot 2 with this case. The infrastructure from this pilot has been uploaded, and all the status is presented here through some graphs and so on. Okay. Oops. Okay. And here you can see everything's okay. So the road, the road is open as it should be. You can see the dashboard that the operator can see in the behind, and also the mobile application and what users could see in case they search for a route or something. You can see here what Theodoris presented, a typical route, the proposed route, no event, nothing. So, okay, here you can start the navigation. Okay. And here we have, let's say, the alert at the traffic control center. We have the alarm received. Okay, I will skip this because I've already presented it before. Okay, and here we have the receipt of the same alert in the resist platform. So as you can see here, you go to the events list, you select the exact asset, and here is the alert prepared from the traffic control center as well. Okay, so then the operator decides to close the road in order to avoid any further, let's say, incidents or accidents, and to prevent risk of users and so on. So the road is closed, the notification is sent to the users, and they also some alternatives for rerouting. You can see here by passing the event area. Okay, and then we can start the inspection of the area that the incident has happened. So as you can see here, this is the task list of the IPM operator. You can select to create a new detailed inspection process, assign specific persons to perform activities, for example, the drone operators, the computer vision operators, and so on. So you create the new inspection. Okay. Okay, and then we have the preparation of the RPAS mission, the drone flight, actually. The drone operator needs, let's say, a flight plan in order to know where exactly to go to fly and what to check. So here we prepare the flight plan with a description, with some points and so on. Okay, you can see here. Okay. The mission is sent to the drone operator. Okay. Here you can see the receipt of this flight plan from the drone operator. He checks it. Maybe something is not correct, so it has the option to reject the flight plan. So in this case, it's like the rejection and also a justification why this flight plan is detected. In this case, some information is missing. So as you can see here, a new flight plan is requested by the drone operator to the IPM operator. So the IPM operator goes again to the same detailed inspection process, receives the justification from the drone operator, and let's say changes the flight plan, prepares a new one. Okay, you can see here the new flight plan with some coordinates, some points, and so on. Okay. Again, the drone operator receives the new flight plan, and now he can confirm that it's okay. You will see here. Okay, the new flight plan is accepted. Okay, and then he can proceed with the flight. So when the operator is ready to start the flight, he also sent that this step is completed and he's ready to start the flight. Okay, and here you can see the flight. As you can see, this is an autonomous flight. The operator does not navigate the drone. He's only for backup in case something goes wrong. Okay, so the drone is flying following the flight plan that has been prepared. During this flight, raw images are collected from the infrastructure that are going to be processed later on. And when the flight plan is finished, the drone is landed. All this through autonomous navigation. Okay. Okay, then the IPM operator goes back to the resist platform and can informs the system that the flight has been finished. So then the raw images, all the data that have been collected, in this case it's images, can be stored. Here you can see the storage of raw images. Okay. Okay, you can store the data to the platform. Okay. And then the system processes these images in order to create some, let's say, metadata and annotated images. So you can see here. It's paused. Sorry, this is paused. Okay, now. Okay, so when the images are processed, the IPM operator informs the system that they have also been uploaded. And here you can see all the information that has been created through this process of raw images. Okay. So you can see here that the validation is proposed by the system. So the IPM operator can go to the photogrammetric, let's say, module and check for the 3D point cloud that has been created of the infrastructure. You will see right now. Okay, here is the 3D model. As you can see, it has been created. This is one surface of the tunnel. Okay, you can zoom in, you can zoom out. Okay, and then you can see also the annotated images, the images that have been collected from the drone, and also some defects have been detected on these images, some cracks or something, some other defects. You can see here, for example, one crack. At the left, there is the list of all defects that have been identified with some information about the coordinates and so on. Okay. And when this is ready, if the operator decides that more measurements are required in order to validate these defects, it can request for a new drone mission, this time with a contact drone, in order to take some ultrasonic measurements and rebar measurements and check that everything is good or needs to be maintained or replaced. Okay, so here we have the new mission. In this case, this is with the contact drone. Okay, again, we create the new mission. Okay. The mission is accepted. Again, there is the possibility to reject it and ask for a new flight plan. Okay, but we skip this part. Okay, and then we are ready to start the flight once again. The new flight with the contact drone. Okay, and here it is. This flight can be done either manually or autonomously. We did both ways. As you can see here, the drone reaches the surface of the tunnel and contacts the surface of the tunnel. And here you can see the footage from the camera. And also you can see the ultrasonic sensor moving at the low right part. Scanning, let's say, the area and getting information. As you can see, each time a defect is identified, the light is flashing. So it scans the whole area that needs to be scanned, getting information from this. And when these measurements are completed, it lands again. Detaches from the surface and then safely lands. Okay, and here we have another similar flight. This is an autonomous flight, actually. You will see also the results of this analysis, the ultrasonic measurements and so on. Okay, so we have the takeoff again. And here you can see the model of the tunnel. Again, it reaches the wall. You can see it also from the shadow of the drone. And then it contacts the surface. And you can see also the footage from the analysis of the measurements from the sensors that are embedded in the drone. Also the angle and so on. Okay, and then when the measurements are completed, the drone lands again. Okay. So based on this analysis and the extra measurements that have been collected, the structural vulnerability and risk assessment can be performed. Here you can see the other module of resist. So you can select the asset. Here the simple Petronilla tunnel is selected. You can see the model. Okay. Oops, sorry for this. This is the area that is marked to be inspected. The results of the measurements and their analysis. Some graphs that are prepared, the areas that maybe need to be further examined or inspected or replaced, and so on. Information that's needed for the maintenance of the infrastructure. Okay. The analysis of the defects. Here you have a crack, some information, coordinates, and their related images, annotated images, and their analysis. Okay. Okay, so when this part is finished, if the operator decides that the infrastructure is not affected and the road can be given back to the operation, then through the dashboard, the operator can reopen the road, reopen the tunnel in this case. So the notification to the users disappears. We will see it. Okay, it disappears. And in case a user researches for this route, the initial route through the tunnel will be proposed again. So this is it. I hope it was interesting. So I think, thank you all. Thank you all. I think that we can now the participants that are here in person. And then we can go to the field to see the actual performance of the drones, the flights and so on. Let me also thank all the participants that have joined online. Thank you all. In case there are any questions, they can be sent to ourselves or through the social media, the site, and so on, or by emails. You have all our mails from the presentations, and we will be happy to answer any question or clarify how Resist aims to, let's say, support the whole infrastructure inspection and maintenance. Thank you all.
Thank you.